why the integral is an infinite sum of rectangular strips and not just the Riemann sum definition. Yeah? Take a look at that sheet, please. So I wrote it on here so that we could save a little bit of time. You wouldn't have to take notes on this. You could just have it put in your notes. Are we all on the same page? This page? Yep. Okay. So for whoever is looking at this, maybe you could take a snapshot of this whenever you're looking at it. There it is. Okay. Oh, no. Okay, see where the two diagrams are at the top? Say yes.
Yes.
We got through that stuff pretty much already. Then it says the mean value theorem. Now we talked about the mean value theorem before. This is called the mean value theorem for areas. I'm going to talk a little fast, so listen fast. Look at the diagram. And I showed you that before. You see the two shaded areas. Part of it is in the rectangle, but not under the curve. The other part is under the curve, but not in the rectangle. Remember that part?
Yeah.
It's got to be some C so that f of C is just right. So the area of the rectangle is going to be exactly the same as the area of the curve. We all understood that on Friday, yeah?
Yes.
You're all focusing on this, yeah? Okay. So area from A to B, therefore, is f of C times B minus A. The area from A to B represents the area under the curve from A to B. So there's another diagram, number 4. See it? Diagram 4, where it's the same idea, but except this time, you're looking at an area that goes from A to X. So that X could be any number. You want to go from 3 to 4 now, I want to go from 3 to 7. I want to be able to get the area from anywhere I want to anywhere I want. So therefore, once we go area from A to X, that becomes a function of X. It's not a finite area. From 2 to 3 would be an area, a numerical area. From A to X is, I don't know, depends on X. Capiche? So that's a function of X. Because it's a function of X, we're going to differentiate that function. Now this is a made-up function. Area from A to X. And therefore, if I ask you, all right, what's the derivative of area at X, you're not going to know. But we can always go back to the definition of the derivative. And that's what we're doing here. Derivative from area to X, see it? D dx. What's on the right side? Limit as delta X goes to 0. And does the numerator of that fraction make sense? Remember f of x plus h minus f of x over h? Except h this time is delta x. It's just a definition. Yes, Josh? A little louder, Josh.
I don't understand, like, why can't you just substitute x plus delta x for...
Let's just look at the area. Now look at diagram 4.
Yeah.
We're interested in a rectangle whose base goes from x to x plus delta x. That's our A and our B.
That makes sense.
And there's C. There's a C in that little space also. So now I'm using, yes.
What is representing delta x? And what
Could you speak louder, please?
What is representing delta x and what is representing x?
Delta x is the space between x. We're looking at diagram 4, yes? Delta x is the base of that little rectangle, that skinny, tall rectangle. That's what delta x is.
What
X is just an x value, an arbitrary x value.
Which one is
The one in the diagram, there's an arrow pointing to it. No, there aren't two, there's one. We're looking at diagram 4. It goes from A to X. That's the only X. So this thing over here is really our delta X. That's why this point here is X plus delta X. Then they're creating a rectangle. There's a C in there somewhere that makes the area from X to X plus delta X. That's the area. From X to X plus delta X. That's his little thing. So we have the area from A. Again, we're looking at the first line of the derivative from A to X plus delta X. And then the next line you see I've split it into a sum of two areas. It still says take away the area from A to X. That was in the first line. How many understand why the area from A to X plus delta X can be written as a sum of two areas? 2 people, 3 people, most people. All we're doing, look at the diagram, is saying the area from A all the way to X plus delta X can be written as the area from A to X plus the area from X to X plus delta X. Yeah? In that numerator, there was a subtraction. Take away the area from A to X. It's still there in the numerator. Subtract it. And all you're left with, move to the right, all you're left with is what in your numerator? Now look at the right of that. By the mean value theorem, that can be represented by some f of c times delta x. Some height at some c value. So now I'm replacing that in the numerator, f of c times delta x over delta x.
Why is it f of c times delta x?
That area from x to x plus delta x is equal to f of c times delta x. This area, the area under the curve from here to there, is equal to some f of c times, that's height, times delta x, base. That's where that delta x came from. So look at that line now. What happens to the delta x? Yes, they do. So all you left with f of c. Now I've changed the limit here. Come back to the diagram, please. Remember, please look here. This is the c value. As delta x approaches 0, smaller, 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 c is getting closer and closer to the first x value. And therefore, as delta x approaches 0, c approaches x. And that's what I've written in the last part of the limit. C approaches x. F of c, as c approaches x, becomes... Therefore, now, so you look at the left of the equation, the derivative of the area function is f of x. What did I do in the next line where it says or? I did something algebra. What do you mean?
Well, you put a differential form by multiplying each side by dx.
Exactly. And then I did something else. So or. Notice now the d area from A to x doesn't have a d anymore. I undid the d. How do you undo multiplication? Subtraction. Derivative. That's why the right side became the integral of fx dx, not just f of x dx. We essentially integrated both sides. I'm going to write that. D area from A to x. This is what we had. The integral on the left side undoes the d. And that's why we left this here. We want to take this one step further. We're almost done. You'll notice to the right of that, and we've been using lowercase now, so it says the answer to that integral is capital F of x, and of course plus a c. That means? And this is, where did I write that? Look at the next to the last line. How do we find c? Look at the diagram, please. Area from A to x. Let's say this is 2 and this is 5. Is there an area there?
Yes.
Suppose it's 2 and 4. What happened to the area? 2 and 2.5. What would you think? Thank you. The area from A to A has to be. So that's what I'm showing you the next to the last line. So if you're going the area from A to A, what you're left with is the area from A to A, which is 0, which is f of A, because x is now an A, plus c. That allows you to find c. A little bit of algebra here in this equation. So So C equals.
Negative.
So if you look at that, it's still the next to the last line. The area from A to X is f of x minus f of a. And now we go to the final stage. When you want to integrate from A to B, of course, it would be f of b minus f of a. This, ladies and gentlemen, is how we, sorry, Captain, is how we evaluate a definite integral. That is the meaning of evaluating a really easy question, x squared dx. Somebody give me a smallish number
Three.
and slightly bigger one.
Five.
Listen, so we're just practicing this process. It's always from smaller to larger. You'll understand why soon once we start applying it. Now this is mechanical. So we're going to now find, that's lowercase. What's capital? Yes.
2x.
What's capital? Yes.
Consider third over 3.
Yes. You went the wrong way. We're integrating. We're integrating x squared. Now normally we write plus c, but actually we have a way to figure out c. Remember c was f of the a value. Yep. Take away. I'm going to indicate it with a notation that looks like this, 3 to 6, just to get us ready to do the plugging in. We're going to do capital F of 6, B, minus F of A. So we're going to be plugging in a 6, 6 cubed over 3, minus 3 cubed over 3. All we're doing is plugging in the values that they gave us in the question. And you know what the answer is? So let's do without counting. Let's do a little arithmetic. Let's move away one of these, factor out one of these 6's, yes? Why would I want to factor out one of these 6's? You got it? Yes. So now you're actually seeing 2 times,
36.
which is,
17.
hold that number. And of course, this is really just,
9.
yes. So remember that other number?
72 minus 9.
Which is,
68.
we've just done our first definite integral. We just learned how to do it. First we derived this. This is the recipe. And it's not that we don't have a plus c, it's that we used it. It's now known. When you see an integral expression with limits of integration, that would be the 3 and 6. We call it a definite integral. No c anymore. We're able to evaluate this. Let me get to another example. Apply it. I'm just going to put this in the tray. The tray is sort of non-existent. What I'd like us to do this time is find the area bounded by this curve in the x-axis for that little integral. What if you were to make a 2-second sketch of the curve? Tell me you're done.
On paper, it's not.
Come on, 2 seconds. That's the cosine. And you only go 0 to pi over 2.
Ah, okay. That's not
Still drawing?
done.
You're not still drawing. How many are done? So you did that. Yeah?
Yeah.
We want to find the area under the curve. We're not going to do an infinite number of rectangular, about that method here. We're just going to say the area.